Hey there, deep dive listener. Ever stared at a complex problem, maybe organizing a crazy schedule or a tangled puzzle, and just felt overwhelmed by the sheer number of possibilities?
Uh-huh. Happens all the time.
Today, we're taking a deep dive into a powerful framework that doesn't just tackle these challenges, it actually redefines how we approach them.
Indeed. We're going to unpack something called Constraint Satisfaction Problems, or CSPs.
CIPs, right.
What's truly fascinating here is how they move beyond simply, trying things until something works.
Yeah, brute force.
Exactly. Instead, they leverage the very structure of the problem itself to find solutions intelligently.
That's right. Our mission today is to show you not just what CSPs are, but why they're so incredibly powerful. We'll explore how different techniques interconnect, reveal surprising patterns that emerge when we break open the black box of problem states, and maybe challenge your understanding of what's truly possible in problem solving.
Sounds good. Get ready for some genuine aha moments, hopefully.
Definitely. Okay, so let's unpack this. In typical problem solving, we often treat problem states like little black boxes you only know if you're in a state or not.
Right. Kind of opaque.
But CSPs completely change that, don't they? How does breaking open that black box fundamentally shift our approach?
It's a fundamental paradigm shift, really. Instead of seeing the entire problem as one giant, indivisible thing.
That black box?
Precisely. CSPs let us break open that box. We treat a state as a collection of individual puzzle pieces, what we call variables.
Variables.
And each variable has its own set of possible values, its domain.
Right, like the pieces you can choose from.
Exactly. And the problem is solved when every variable has a value that satisfies all the defined rules or constraints.
Okay, so variables are the things we need to make decisions about, like, say, regions on a map or tasks in a schedule.
Perfect examples.
And domains are the choices available for each variable, like choosing a color from red, green, blue for the map.
Yep, that's the domain.
And constraints. Those are the rules that connect these variables, like neighboring regions must be different colors.
Exactly. That's the glue holding it all together.
So what's so powerful about this structured approach? I mean, why is this better?
Well, one of the immediate advantages is how naturally many real-world problems fit this model. It just feels right for certain problems.
Okay, that makes sense.
But the real power comes in the fact that CSPs use general-purpose strategies, heuristics, that apply across many different problems.
So not custom-built solutions every time.
Right. And this allows for incredibly efficient pruning.
Pruning, cutting things back.
Yeah. If a partial assignment of values to variables violates a constraint, we can immediately discard all further possibilities based on that bad start.
Wow, okay.
This is far more efficient than traditional search methods, which might just keep going and only ask, is this final state a solution? Much later.
So you catch the mistakes way earlier.
Way earlier. Saves a huge amount of work.
Let's make this tangible. The classic example. Coloring the map of Australia.
A good one.
You've got variables for each state and territory, WA, NT, Q, and so on.
Yep, 7 of them.
The domain for every single one is red, green, blue. 3 choices.
Simple enough.
And the constraints are simple. Neighboring regions must have distinct colors, so SA can't be the same as WA, for example.
Correct. SAEWA, that's a binary constraint.
Now, here's a surprising fact, something that really clicked for me. Once you assign a color, say, you decide South Australia blue.
Okay.
You immediately know that none of its 5 neighbors, WA, NTQ, NSWV, none of them can be blue.
Instantly, the constraint fires.
An ordinary black box search might still explore, what, 3 to the power of 5? 243 combinations for those neighbors.
It would, yes. Blindly trying possibilities.
But with CSPs and our active constraints, you've just slashed the possibilities for those neighbors down to 2 to the power of 5, which is 32.
That's an 87% reduction, just from one assignment.
That's the sheer power of pruning. It's like being able to see through walls in a maze, almost.
That's a great analogy. And to visualize these connections, we often use a constraint graph.
Okay, what's that?
Think of it as a network. Each variable, like a state on the map, is a node, a point.
Right.
And if 2 variables have a constraint between them, like SA and WA needing different colors, you draw an edge, a line connecting them.
So it shows you visually which things affect each other.
Exactly. It helps us see the structure of the problem. For constraints involving more than 2 variables, we might use something called a hypergraph, but the idea is the same.
Gotcha. Visualizing the dependencies.
Now, this structured approach extends to the types of values variables can take and the rules that govern them. This raises an important question. Are all CSPs the same?
I guess not.
No.
Huh.
Not all domains or constraints are created equal, and understanding their variations is crucial. We commonly deal with discrete, finite domains, like our map colors, red, green, blue, or maybe choosing an integer row for a queen on a chessboard, 1.8.
Finite choices. Okay.
But we can also have discrete, infinite domains. Imagine scheduling jobs without an end date. The start time could be any integer.
Whoa. How do you handle infinite possibilities?
You need implicit constraints, like mathematical relationships, say T1 plus duration 1 must be less than or equal to T2. You can't list all the allowed pairs.
Okay, that makes sense. And continuous.
Right. Continuous domains where values are precise, real numbers. Think complex scheduling like planning observations for the Hubble Space Telescope. Timings have to be exact. Linear programming often deals with these.
So a lot of flexibility in the types of values. What about the constraints themselves?
They vary too. You have simple unary constraints that restrict just a single variable.
Like maybe South Australia just can't be green for some reason.
Exactly. SAA green, that's unary. Even the initial domain, red, green, blue, is technically a set of unary constraints.
Okay.
Then binary constraints relate to variables, like our map example, SAA NSW. Problems with only unary and binary constraints are called binary CSPs. They're quite common.
And higher order.
Yep. Higher order constraints involve 3 or more variables. Maybe a rule like task Y must happen between task X and task Z. That's ternary.
Okay.
And even more powerfully, global constraints. These are special higher order constraints that apply to an arbitrary number of variables, often encapsulating a common pattern.
Like what?
The all-diff constraint is a prime example. It requires all variables in a set to have different values.
Ah, like in Sudoku. Every row, column, and box needs unique number.
Exactly. That's pure all-diff. Another common one is a resource constraint, or sometimes called at most. It limits the total usage of something, like saying at most 10 personnel can be assigned across tasks P1, P2, P3, and P4.
So you sum up the requirements.
Precisely.
Yeah.
Flexibility to define these different types of domains and constraints means CSPs can be molded to fit almost any problem you can imagine. It's a really versatile framework.
That's quite the toolbox. And it goes even further, right? I read you can actually transform complex constraints.
Yes, that's a key technique. You can actually take any finite domain constraint, even one involving many variables, like an n-ary one, and break it down into a set of simpler binary constraints by introducing some extra auxiliary variables.
Why would you do that?
It often simplifies the algorithms needed to solve the problem. Many algorithms are designed specifically for binary constraints. There's also another trick called the dual graph transformation that does something similar.
Interesting. And CSPs aren't just for finding if a solution exists, right? What if some solutions are better than others?
Good point. You can add preference constraints. Maybe assigning a certain color costs more, or finishing a task earlier is better. You assign costs or utilities to variable assignments.
So it becomes an optimization problem.
Exactly. It turns the CSP into a constrained optimization problem, or COP. Then you use optimization search methods to find the best solution according to your preferences, not just any solution.
That opens up a whole new level, finding the optimal assignment.
It does. Very powerful in practice.
Okay, so far we've talked about setting up the problem variables, domains, constraints, all the different types. But what happens during the search for a solution? You mentioned pruning, but it seems like there's more to it. It's not just about blindly trying values. It's about making smart deductions as you go. This is where constraint propagation comes in, right? How does this intelligent deduction actually work?
Constraint propagation is really a form of inference. Active inference. It uses the rules, the constraints, to actively reduce the number of legal values for a variable.
Okay.
The key thing is, reducing the choices for one variable can then trigger reductions for other variables connected by constraints. It cascades through the problem.
Like ripples in a pond.
Exactly. The core idea is local consistency, by making sure small parts of the problem graph are consistent with the constraints.
Like pairs or triples of variable.
Yes, like pairs for arc consistency, or just single variables for node consistency. By enforcing consistency locally, we can eliminate inconsistent values throughout the entire problem.
So what's arc consistency again? That sounds important.
It's probably the most common form. Imagine two variables, x and y, connected by a constraint. X is arc consistent with y if for every possible value left in x's domain, there's at least one compatible value still available in y's domain that satisfies their shared constraint.
So if a value in X has no compatible partners left in Y, then that value in X can't possibly be part of a solution.
Precisely. So you can just remove it from X's domain immediately.
And that might then affect other variables connected to X.
Yes, that's the propagation. Algorithms like AC3 manage this process, keeping track of arcs that need checking. And the remarkable thing is, if this process causes any variable's domain to become empty,
No values left.
no values left, then we know, right then and there, there's no solution to the entire CSP. The algorithm can just stop and report failure.
Wow. That's incredibly powerful, detecting failure early just through propagation.
It is. It saves exploring potentially vast, fruitless search spaces. There are stronger forms too, like path consistency looking at triples, but arc consistency is a common workhorse.
And we all know an amazing example of this in action, Sudoku.
Ah, yes, the classic CSP benchmark.
It's a perfect CSP, isn't it? Each square is a variable
81 of them.
with numbers 1 to 9 as its domain, if it's empty.
Right.
And the rules of Sudoku are simply those 27 all-diff global constraints we mentioned earlier.
Yep, 9 for each row, 9 for each column, and 9 for each 3x3 box. All variables in each set must be different.
What's fascinating is that the core ideas of arc consistency, implemented in algorithms like AC3, can often solve easy Sudoku puzzles by themselves.
That's right. Just by propagating those all-diff constraints, eliminating possibilities, sometimes a square's domain shrinks down to just one single number.
Problem solved for that square.
Exactly. And all those human strategies you hear about, like naked triples or hidden pairs that expert Sudoku players use, they're essentially sophisticated manual ways of enforcing consistency for these all-diff constraints. They're discovering implications that propagation would find.
That's brilliant. It truly shows the power of defining a problem correctly, framing it as a CSP, and then letting these general, powerful mechanisms take over.
It really does. The representation is key.
Okay, but even with all that powerful deduction, sometimes propagation isn't enough, right? You might still have variables with multiple possible values left.
Absolutely. Propagation often simplifies the problem, but rarely solves it completely on its own, especially for harder problems. That's when we need to actually search.
And the main way is backtracking search.
That's the standard systematic approach. It's a form of depth-first search where we build partial solutions step by step. Assign a value to a variable, move to the next, assign a value.
And if you hit a dead end,
You backtrack.
Yeah.
You undo the last assignment and try a different value. If you run out of values, you backtrack further up.
Okay. Now, what's crucial here, you mentioned, is that in CSPs, the order in which you assign variables doesn't affect the final solution.
Yes, commutativity. Super important. If assigning red to WA, then blue to NT is part of a solution, then assigning blue to NT, then red to WA could also lead to the same solution.
How does that help?
It means at each step in the search, we only need to decide which variable to assign next, not worry about permutations of the order. This drastically shrinks the potential search space compared to general search problems.
Right, that makes sense. So how do we make that search as efficient as possible? We need smart strategies, heuristics, right?
Exactly. We need heuristics to decide two things at each step. Which variable to assign next, and which value to try first for that variable.
Okay, variable first. What's the strategy?
The most common is the minimum remaining values heuristic, or MRV.
Minimum remaining values.
It tells us to pick the unassigned variable that has the fewest legal values left in its domain.
Why? That seems counterintuitive, picking the hardest one.
It's sometimes called the fail-first heuristic. The logic is, if a variable is down to only one or two options, it's highly constrained. If assigning a value there is going to lead to a contradiction.
You want to find out sooner rather than later.
Exactly. Find the failure early to prune that entire branch of the search tree. Don't waste time exploring stuff that's doomed because of this bottleneck variable.
Clever. And if there's a tie in MRV, two variables both have only two values left.
Good question. Then we'll use a tiebreaker, usually the degree heuristic.
Agree, like in the constraint graph.
Precisely. It suggests picking the variable that is involved in the largest number of constraints with other unassigned variables.
Why that one?
The idea is that assigning this variable will likely have the biggest impact on restricting the choices for its neighbors, hopefully pruning the future search space more effectively.
Okay, so MRV first, then degree heuristic as a tiebreaker. That's for which variable. Now, what about which value to try first for that chosen variable?
Here, the strategy is often the opposite. We use the least constraining value heuristic.
Least constraining.
So the easiest value.
Kind of. It recommends picking the value that rules out the fewest choices for the neighboring, Still unassigned variables in the constraints.
Ah, so you try to keep options open for the future.
Exactly. The idea here is to leave as much flexibility as possible for subsequent decisions, increasing your chances of finding a solution path quickly without painting yourself into a corner.
Okay, this raises that interesting question again. Why does it make sense to pick the variable most likely to fail first, MRV, but the value that is least constraining the one most likely to let you succeed, LCV? That feels like a contradiction.
It does seem like one at first, but it's actually a very clever balance. Think about it. For variable selection,
Right.
every variable must eventually be assigned some value. So by tackling the most constrained ones first, MRV, you find inevitable failures quickly, pruning the search.
It's a bad news early. Right. But for value selection, you typically only need to find one valid solution. You don't need to explore all possibilities for a variable. So by trying the least constraining value first, LCV, you maximize your chances of staying on a path that leads to a solution.
Okay, that clarifies it. One optimizes for finding failures fast, the other optimizes for finding success fast.
You got it. It's about efficiently navigating that search tree.
We can also layer more intelligence onto this search, right? Doing inference during the search.
Yes, we don't just assign and check. Forward checking is a simple but effective technique.
How does that work?
When you assign a value to a variable, say x equals red, forward checking immediately looks at all unassigned neighbors of x,
Like Y and Z.
and it deletes any values from their domains that are now inconsistent with x red. So if y had red blue and was constrained to be different from x, forward checking would immediately remove red from y's domain, leaving only blue.
So it anticipates immediate conflicts.
Exactly. It also provides great information for the MRV heuristic on the fly.
And there's something stronger. MAC.
Yes, maintaining arc consistency, or MSC. It's more powerful. After assigning a value to x, instead of just checking immediate neighbors, it basically reruns an arc consistency algorithm, like AC3, starting from x.
So it propagates the consequences much further.
Much further, recursively ensuring arc consistency throughout the relevant part of the graph after each assignment. MSC detects more inconsistencies earlier than plain forward checking, but it also costs more computationally per step.
Trade-offs again.
Always trade-offs.
Now, what happens when a search branch does fail? We have to backtrack. But can we do that smartly?
Absolutely. Simple chronological backtracking just goes back to the immediately preceding variable and tries its next value. But that's often inefficient.
Why?
Imagine trying to color Australia. You assign some colors on the mainland, then color Tasmania, then find a conflict back on the mainland involving South Australia. Chronological backtracking might try changing Tasmania's color.
Which is useless, because Tasmania isn't connected to South Australia.
Exactly. It's irrelevant to that conflict. So smarter techniques were developed. Backjumping analyzes the reason for the failure, the conflict set of assignments that caused a variable's domain to become empty.
Okay.
And it directly jumps back to the most recent variable in that conflict set, potentially skipping over many irrelevant intermediate decisions, like Tasmania in our example.
That sounds much better.
There's also conflict-directed backjumping, which is even more sophisticated in identifying the root cause of the conflict, allowing for potentially even larger jumps.
And can we learn from these failures so we don't make the same mistake again?
Yes, that's constraint learning or recording no goods. When a contradiction is found, the system identifies the subset of assignments that caused it. This inconsistent partial assignment is a no-good.
Like a little forbidden pattern.
Exactly. The system can then record this, perhaps by adding a new explicit constraint or just caching it. This prevents the search from re-exploring other branches that contain this same doomed combination of assignments later on. It's crucial for the efficiency of modern CSP solvers.
Okay, so backtracking search with heuristics, inference, and intelligent backtracking learning. That's one major approach. But there's a completely different paradigm too, right? Local search.
Yes, a very different way of thinking. Instead of building a solution piece by piece from scratch like backtracking, local search starts with a complete assignment for all variables. It might be random, so it probably violates many constraints initially.
Okay, so it's a full but broken solution.
Exactly. Then it iteratively tries to improve this assignment by making small changes, usually focusing on the violated constraints.
How does it decide what to change?
The most common heuristic here is min conflicts. It's beautifully simple.
Okay.
At each step, you randomly pick a conflicted variable one that's involved in some violated constraint.
Right.
Then you look at the values in its domain, and choose the value that minimizes the total number of constraints violated across the entire assignment. You reassign the variable to that best value.
So you just try to reduce the number of conflicts locally?
Yep. Just keep doing that. Pick a conflicted variable, change its value to the one causing the fewest conflicts.
Right.
Repeat.
Does that actually work? It sounds almost too simple.
What's truly surprising is how incredibly effective min conflicts can be, especially on certain large problems. For the n-queens problem, placing n-queens on a nay-n chessboard so none attack each other.
Yeah, a classic CSP.
Min conflicts can solve massive instances, like the 3,000 queens problem in under a minute, starting from a random assignment.
3 million queens in a minute.
Yeah. This surprising efficiency really stimulated a lot of research into why some problems seem easy for algorithms like this, while others are hard.
Any other examples?
It famously was used to schedule observations for the Hubble Space Telescope. What was previously a 3-week manual planning task by experts could be done by min conflicts in about 10 minutes, often finding better schedules.
That's incredible, reducing weeks to minutes.
It really highlighted the power of the approach. Of course, local search can get stuck
In a local minimum, where any change makes things worse, but it's still not a solution.
Exactly. Or on a plateau where adjacent states have the same number of conflicts. So there are techniques to escape these traps.
Like what?
Taboo Search keeps a short list of recently visited states to avoid immediately cycling back to them. Simulated annealing allows some bad moves that increase conflicts probabilistically, hoping to jump out of a local optimum.
A bit of randomness to a state.
Right. And constraint weighting is another clever idea. You assign weights to constraints, and whenever a constraint is violated, you increase its weight. The search then tries to minimize the sum of weights of violated constraints.
So it learns which constraints are hardest to satisfy and focuses more effort there.
Precisely. It dynamically adjusts the search landscape. Local search is also fantastic for dynamic problems.
Like what?
Like needing to repair an airline schedule quickly after bad weather causes disruptions. You want to find a new, valid schedule with minimal changes to the existing one. Local search is great for that kind of online repair.
Okay, so 2 main families. Backtracking, systematic, complete, and local search. Iterative improvement, often incomplete but very fast.
That's a good summary.
Now here's where we really connect the dots, I think. We've talked about setting up the problem and searching for solutions, but it turns out that how you structure or represent your problem, particularly its underlying constraint graph, can be the ultimate shortcut.
Absolutely. This connects to the bigger picture. The inherent graph structure can radically change the complexity. What looks intractable might become easily solvable if you spot the right structure.
Like independent subproblems.
Exactly. If your problem's constraint graph naturally falls apart into completely separate chunks.
Like our Tasmania example earlier, being disconnected from mainland Australia on the map coloring constraint graph.
Perfect example. Tasmania forms its own independent subproblem. The coloring choices there have zero impact on the mainland, and vice versa.
So you can just solve them separately.
Completely separately. Solve the mainland coloring, solve the Tasmania coloring, and then just combine the solutions.
And that's a big deal computationally.
It's a massive efficiency gain. Suppose you have n variables total, but they break into, say, k independent subproblems, each with roughly n variables, instead of the cost being exponential in n, like d to the power of n.
Which gets huge fast.
The total work becomes roughly k times d to the power of n. If k, the size of the subproblems, is much smaller than n, the difference is astronomical.
Give me a sense of that.
Okay, think about it. Dividing a Boolean CSP, or D2, with 100 variables into 4 independent subproblems of 25 variables. You reduce the worst-case solution time from something like the lifetime of the universe down to less than a second.
Wow. Just by noticing the graph is disconnected, that's a profound pattern.
It really is. Structure is power.
And even if it's not completely separate, what if the structure is simpler, like a tree?
Tree-structured CSPs. Those are special. A constraint graph is a tree if there's only one path between any 2 variables. No loops or cycles.
Okay, why are they special?
Because they can be solved incredibly efficiently. In time, that's linear in the number of variables, specifically OND2, where n is variables and d is domain size.
Linear time, so no exponential blowup.
No exponential blowup, and crucially, you don't need backtracking.
No backtracking at all. How?
There's a clever algorithm based on achieving directional arc consistency, DAC. You first order the variables, kind of like a parent-child relationship in the tree, Then you process the variables from the leaves up to the root, making sure each variable is arc consistent with its parent.
Okay, bottom-up consistency pass.
Right. Once you've done that, you can simply assign values starting from the root variable and going down towards the leaves. Because of the enforced DAC, you're guaranteed to find a consistent value at each step without needing to backtrack.
That's elegant. So if your problem is a tree, you're golden.
Pretty much, yes.
But what if your problem isn't naturally a tree? Most real-world problems probably have cycles in their constraint graphs. Can we still somehow leverage this tree idea?
Yes, we can transform or decompose the problem to exploit tree-like properties, even if the original graph isn't a tree. One major technique is cutset conditioning.
Cutset conditioning, what's that?
The idea is to find a small set of variables called a cycle cutset, such that if you remove these variables and their constraints temporarily, the remaining constraint graph becomes a tree.
Ah, like finding a few key nodes that break all the loops.
Exactly. In our Australia map, South Australia is connected to almost everything on the mainland, if you remove SA.
Let me picture that.
Yeah.
The rest, WA, NT, Q, NSW, V, looks more like a line or a tree structure. SA is the key connector causing cycles.
Right, so SA could be our cycle cutset, in this
Okay.
case size C1.
So what do you do with this cutset?
You iterate through all possible consistent assignments of values just for the variables in the cutset. For our example, try SA red, then SA green, then SA blue.
Okay.
For each of these assignments to the cutset, like SA red, you propagate the consequences. Remove any inconsistent values from the domains of the remaining variables. Now, the remaining problem is tree structured.
And we know how to solve trees efficiently.
Exactly. So you solve the remaining tree problem. If you find a solution, you combine it with the cutset assignment, and you're done. If not, you try the next cutset assignment, SA green, and so on.
What's the complexity?
It depends heavily on the size C of the cutset you find. It's roughly ODC in CD2. If you can find a small cutset, small c, this can be much, much better than ODN for the original problem.
But finding the smallest cutset is hard.
Finding the absolute minimum cycle cutset is NP hard itself, yes. But often, good heuristics can find reasonably small ones. A big advantage is that cutset conditioning uses memory that's only linear in N.
Okay, linear memory, that's good. Is there another way to reduce to trees?
Yes, tree decomposition. This is a bit more abstract. It transforms the original graph into a new graph that is a tree. But the nodes in this new tree aren't single variables anymore.
What are they then?
Each node in the decomposition tree represents a subset of variables from the original problem, essentially a subproblem. These subsets have to overlap in specific ways to ensure all original variables and constraints are covered, and maintain a kind of consistency along the paths in the tree.
That sounds complicated. What's the benefit?
The key measure is the tree width, WTEP. It's related to the size of the largest subset of variables in any node of the optimal decomposition tree, specifically size 1. If a graph has a bounded tree width WF, the original CSP can be solved in time, ON dW plus 1.
So polynomial time if the tree width is fixed, even if Feynman grows?
Yes, for bounded tree width. And often the tree width LWF can be significantly smaller than the cutset size C-1, potentially leading to better theoretical time complexity.
But there's a catch.
The catch is memory. Solving via tree decomposition generally requires memory that is exponential in the tree width W.
Ah, so cutset conditioning is linear memory, but might be slower time-wise depending on C. Tree decomposition might be faster time-wise depending on W2, but needs exponential memory.
Exactly.
Yeah.
It's a classic time versus space trade-off. Which one is better depends on the specific problem structure and available resources. Finding the optimal tree decomposition is also NP hard, by the way.
Of course it is. Okay, one last structural thing, value symmetry. What's that about?
Sometimes the problem has symmetries where you can swap values around and still have a valid solution. In map coloring, with red, green, blue, if you find one valid coloring, you could swap all the reds for greens and all the greens for reds, and you get another valid coloring.
Right, it's essentially the same solution, just with different labels.
Exactly. This is value symmetry. It means the search space contains many redundant equivalent solutions.
Can we get rid of that redundancy?
Yes, by introducing a symmetry breaking constraint.
Like what?
For the map coloring, you could add an arbitrary constraint like assign the colors alphabetically to the first few territories. Maybe enforce WA, NTSA lexicographically based on their assigned color names, blue, green, red.
So you couldn't have WA green and NT blue, for instance, if that violates the order?
Precisely. This simple extra constraint eliminates all those symmetric copies of solutions, forcing the search to only find one representative from each symmetry class.
And that helps efficiency.
It can significantly reduce the search space, sometimes by a factor of d factorial, where d is the number of values being swapped, like the number of colors. That could be a huge saving.
Wow. Okay, we've covered a lot of ground.
We really have.
We've truly taken a deep dive today, haven't we? From the foundational concepts of constraint satisfaction, problems, variables, domains, constraints, and their varied forms,
Discrete, continuous, unary, binary, global.
to the nuanced power of constraint propagation, like arc, consistency, and AC3.
Using inference to prune the search
The
space.
smart strategies of backtracking search with heuristics like MRV and LCV, and intelligent backtracking.
And the whole different world of local search with min conflicts.
Right. And finally, how understanding and manipulating the problem structure, finding independent subproblems, exploiting trees with conditioning or decomposition, breaking symmetries can yield just astonishing efficiency gains.
It really highlights that for many complex challenges, the breakthrough isn't just in raw computational power, though that helps,
Yeah.
but in how intelligently we represent and reason about the problem itself, using the structure, using the constraints actively. You now have a powerful framework for thinking about problems of assignment and constraint.
Exactly. The fact that problems once considered completely intractable, like that Hubble scheduling example going from 3 weeks of manual effort down to 10 minutes.
Just by reformulating it as a CSP and applying these kinds of techniques.
It just shows the power. So what does this all mean for the future? This raises an important question. Could applying these deep dive methods, this CSP thinking, to other seemingly intractable problems, maybe designing complex molecules or optimizing global supply chains or even for environmental modeling, could it reveal hidden solvable structures there too?
It's certainly possible. The framework is very general. The challenge often lies in finding the right representation, the right variables and constraints.
Perhaps the ultimate challenge isn't always the problem itself, but our chosen representation of it, finding that key structure that unlocks the solution.
That's a great way to put it. How you frame the problem can be everything.
Something to chew on until our next deep dive.